Right now, as you sit here, light from the deepest past of the universe is crossing space toward us. Most of it began its journey billions of years ago, long before Earth formed, long before the sun ignited. For most of human history, that ancient light remained invisible. Then a new telescope opened its mirrors, and suddenly, the early universe began to appear. But something strange showed up in those images. Something massive. Picture a time when the universe was still young, only a few 100 million years old. Galaxies were small. Matter was still gathering. The first stars had only recently begun to shine. In that early era, black holes were expected to be tiny, small seeds, growing slowly across cosmic time. But the telescope saw something that did not follow those rules. A black hole already enormous, so large that, according to our current models, it should not have existed yet. Pause for a moment, because if this observation is correct, it means something in our understanding of the early universe may be incomplete. And the deeper scientists look, the stranger the timeline becomes. The question is simple: how did something so massive appear so early? The answer, it turns out, leads into one of the most puzzling mysteries modern astronomy has faced. And the story begins with a mirror floating 1,000,000 miles from Earth. There is a mirror floating in space right now. It sits nearly 1,000,000 miles from Earth, far beyond the orbit of the Moon, drifting around a quiet gravitational balance point known as Lagrange Point 2. From that distant location, it looks outward into the deepest darkness we can observe. This machine is the James Webb Space Telescope. Picture something the size of a tennis court unfolding in slow motion in the cold of space. Gold mirrors locked together like hexagonal tiles, a giant sunshield stretched wide like a silver sail, always facing the sun so the telescope can remain hidden in permanent shadow. It had to be cold, extremely cold, because Webb was built to see something most telescopes cannot: ancient light. Pause for a moment and think about that. Every star, every galaxy, every glowing cloud in the universe sends light outward in all directions. But light is not instantaneous. It travels at a fixed speed, about 300,000 kilometers every second. Fast, but not infinite. So when light travels across vast distances, it takes time. Sometimes, an incredible amount of time. If a star is 10 light years away, the light reaching your eyes tonight left that star 10 years ago. If a galaxy is 1 billion light years away, the light we see today began its journey when Earth itself looked very different. And when astronomers point a telescope far enough into space, they are no longer just looking across distance. They are looking back into history. The deeper we see, the further back in time we go. This is one of the strange but beautiful rules of the universe. Telescopes are time machines, and Webb was designed to push that idea further than any telescope before it. For decades, astronomers wanted a way to see the first galaxies that ever formed, the earliest structures that appeared after the universe emerged from darkness. But there was a problem. The oldest light in the universe has been stretched. As the universe expands, the wavelengths of light traveling through it slowly grow longer. What began as visible light billions of years ago becomes something different by the time it reaches us. Infrared, light we cannot see with our eyes. Older telescopes, like the Hubble Space Telescope, were powerful but limited. They could see deep into space, but the faintest and oldest galaxies were often beyond their reach. Webb was built to solve that. Instead of focusing only on visible light, Webb was designed to specialize in infrared wavelengths. Think of it like listening for echoes through thick fog. If visible light is like a bright flashlight beam, infrared is more like heat drifting through darkness. Webb listens for that faint glow. And because the earliest galaxies are so distant, their ancient light arrives almost entirely in the infrared spectrum. This meant Webb could see farther back in time than any telescope ever built. When the telescope launched in December of 2021, the mission had one primary goal: look toward the beginning. Astronomers wanted to see the first generations of galaxies forming just a few 100 million years after the Big Bang. Not mature galaxies like our own Milky Way, Small ones, primitive, irregular shapes made of the universe's first stars. Imagine early cosmic construction sites. Clouds of hydrogen slowly collapsing under gravity. Small clusters of stars igniting for the first time. That is what scientists expected to see. The early universe should have looked messy, incomplete, still assembling itself. But before Webb could even begin observing, an extraordinary challenge unfolded. Because the telescope did not arrive in space fully assembled, it had to unfold. Picture launching something the size of a tennis court inside a rocket, faring only 5 meters wide. Every mirror segment folded inward. The massive sunshield packed into layers thinner than paper. Once in space, over the course of 2 weeks, hundreds of mechanical steps had to occur perfectly. Panels opened, structures extended. The giant sunshield stretched outward layer by layer. One small mistake could have ended the mission. Pause and picture the tension inside mission control. This telescope had taken more than 2 decades to design and build, and now it had to deploy flawlessly in the vacuum of space, nearly 1,000,000 miles away, where no astronaut could reach it. Slowly, step by step, the pieces unfolded. First, the solar array, then the communications antenna, then the enormous 5-layer sunshield, each layer stretched tight, separating heat from cold. On one side, the Sunday. On the other side, darkness. Webb needed that darkness, because heat is the enemy of infrared observation. Even the warmth of the telescope itself could blur the faint signals it was trying to detect. So Webb cooled, colder and colder, eventually reaching temperatures near -230 degrees Celsius. Now the mirrors could begin their work. 18 gold segments, each carefully adjusted by tiny motors, aligned themselves with incredible precision. Together they formed a single reflective surface, 6.5 meters wide, more than 2.5 times larger than Hubble's mirror. That meant Webb could gather far more light, faint light, ancient light. And finally, after months of calibration, the telescope turned its gaze outward. Astronomers selected regions of space that appeared almost empty. Small dark patches where few nearby stars blocked the view. These quiet regions allow telescopes to peer deeper than usual, capturing galaxies so distant their light has been traveling across the universe for billions of years. The first deep observations began. Scientists waited. Data arrived slowly. At first, the images looked familiar. Clusters of galaxies scattered across darkness. But something was different. Picture looking at a photograph and realizing the details are sharper than anything you have seen before. Webb's images revealed galaxies that had never been detected. Thousands of them, some extremely faint, some incredibly distant. Each tiny smudge of light represented billions of stars, entire galaxies, many of them forming when the universe was less than 1 billion years old. Astronomers expected these early galaxies to appear small and irregular, but some of them did not. Some looked surprisingly bright, surprisingly organized, and hidden inside a few of those galaxies, there were signals that caught scientists completely off guard. Energy signatures coming from their centers, the kind of signals produced when enormous amounts of matter fall into a black hole. At first, researchers assumed something simple: measurement error, misinterpreted data. After all, the early universe was supposed to be quiet compared to the cosmic structures we see today. Supermassive black holes take time to grow, hundreds of millions, even billions of years. Yet here, inside galaxies that existed very early in cosmic history, Webb seemed to be detecting something unexpected. Black holes already active, already feeding, already massive. That should not have been possible, but the data kept repeating the same signal. And the deeper scientists looked into the observations, the more uncomfortable the numbers became, because if those measurements were correct, they suggested something extraordinary. Some of the largest black holes in the universe may have appeared far earlier than anyone predicted, and that realization was only the beginning of a much larger mystery. When astronomers say they are looking deep into space, they are really saying something stranger. They are looking into the past, not metaphorically, literally. Every beam of light that reaches a telescope has been traveling across the universe for a certain amount of time. The farther away the source is, the longer that light has been on its journey. Picture a message sent across a vast ocean in a glass bottle. The farther the bottle drifts, the longer it takes to arrive. Light works in a similar way, except instead of water currents, it moves through the expanding fabric of space. Pause for a moment and imagine what that means. If a galaxy sits 1 billion light-years away, the light arriving at our telescopes tonight began its trip when life on Earth was still evolving in the oceans. If another galaxy sits 10 billion light-years away, the light we observe today started moving across space long before our sun even existed. Astronomy is the only science where distance becomes time. The deeper you look, the further back the story goes. Now picture stretching that idea to its limit. The universe itself began around 13.8 billion years ago, in the event we call the Big Bang. In the earliest moments after that beginning, the universe was not filled with stars or galaxies. It was an extremely hot, dense sea of particles and radiation. Everything was bright. Everything was chaotic. But as the universe expanded, it began to cool. Within the first few minutes, the simplest atoms formed mostly hydrogen and helium. Then the universe entered a long, quiet period. Astronomers call this time the cosmic dark ages. For millions of years, the universe contained vast clouds of gas, but no stars yet shining to light the darkness. Imagine a night sky with no stars at all, no galaxy, just endless darkness, filled with invisible gas. Gravity slowly began shaping that darkness. Tiny fluctuations in density, small regions, where matter was slightly more concentrated, started pulling surrounding gas toward them. Over time, those regions grew heavier, denser, hotter. Eventually, the pressure became strong enough to ignite nuclear fusion. The first stars were born. Scientists believe this happened roughly 100 to 200 million years after the Big Bang. These early stars were not like the Sunday. They were enormous, many times larger, and they lived short, violent lives. When they exploded as supernovae, they scattered heavier elements across space: carbon, oxygen, iron, the ingredients needed to build planets and life. Those first stars gathered into small clusters. Then clusters grew into the first galaxies. Picture small islands of light forming in a vast dark ocean. That period in cosmic history is often called the Cosmic Dawn, and this is exactly the era the James Webb Space Telescope was built to study. Astronomers hoped Webb would reveal what those early galaxies looked like. They expected something very primitive. Young galaxies should appear small and chaotic, stars forming quickly, gas clouds colliding, structures still assembling. Think of a city under construction, scaffolding everywhere, buildings half finished, nothing fully organized yet. That was the expectation for the early universe. But when Webb began collecting its first deep observations, the images suggested something slightly different. Some of the distant galaxies did not look like messy construction sites. They looked developed, brighter than expected, larger than expected. This alone surprised astronomers. But another mystery soon followed, because galaxies are not just groups of stars. Most galaxies contain something else at their centers, something enormous, a supermassive black hole. Our own galaxy, the Milky Way, has one called Sagittarius A*. It sits at the center, 4 million times more massive than the Sunday, but it took billions of years for that object to grow. Black holes usually begin their lives when massive stars collapse at the end of their lives. The collapsing core forms an incredibly dense object whose gravity becomes so strong that not even light can escape. That is the birth of a black hole. At first, those stellar black holes are relatively small, maybe 5 or 10 times the mass of the Sunday. Over time they grow, they pull in gas, they merge with other black holes. Gradually, they become larger. Imagine a snowball rolling down a hill. At first it is small, but as it rolls, it gathers more snow and grows. Black holes grow in a similar way, except the process usually takes an extraordinary amount of time, hundreds of millions of years, sometimes billions. This is why astronomers expected the earliest galaxies Webb observed to contain either very small black holes or none at all. There simply should not have been enough time yet for them to grow large. But Webb's observations were beginning to hint otherwise. Inside some distant galaxies, astronomers noticed unusual brightness coming from the central regions. At first glance, it looked like intense star formation. Young galaxies can produce enormous bursts of new stars, but the pattern of light was slightly different, more concentrated, more energetic. Think of a lighthouse shining through fog, a single focused source instead of scattered glow. These signals suggested something very powerful might be happening at the centers of those galaxies. Scientists began examining the spectra of the light. Spectroscopy breaks light into its component wavelengths, revealing the fingerprints of different physical processes. When matter spirals into a black hole, it forms a disk of extremely hot gas. This gas glows brightly and produces specific spectral signatures. Those signatures started appearing in Webb's data, over and over again. Now imagine sitting in a research office late at night, looking at those numbers. You expect to see young galaxies. You expect small objects. Instead, the signals begin suggesting something much larger, something feeding, something massive. Pause for a moment and think about the implications. If those signals truly came from black holes, it meant that some galaxies, only a few 100 million years after the Big Bang, already contained objects, millions of times the mass of the Sunday. That should not have been possible. Even if a small black hole had begun growing the moment the first stars exploded, the math simply did not allow it to reach that size so quickly. Something in the timeline was not lining up. At first, scientists suspected the simplest explanation. Maybe the distances were miscalculated. Maybe the galaxies were closer than they appeared. If they were closer, they would also be older. That would solve the problem. But further observations did not support that idea. The distances were correct. The light had traveled more than 13 billion years, which meant those galaxies truly existed when the universe was still in its infancy. And if the signals were accurate, those galaxies already contained extremely large black holes. That realization introduced a troubling possibility. Perhaps the early universe formed structures much faster than our models predict. Or perhaps black holes can grow in ways we do not yet understand. Either explanation would reshape our picture of cosmic history. But the deeper scientists examined the data, the stranger the numbers began to look. Because one particular observation stood out above the rest. A black hole so massive and so early that, according to current theory, it simply should not exist. When the first batches of data from the James Webb Space Telescope arrived, the excitement inside astronomy departments was difficult to describe. New telescopes always reveal something unexpected. But Webb was operating in a completely different league. Its mirrors were larger, its instruments more sensitive, its view deeper than anything humanity had ever built. Scientists began examining the first deep field observations almost immediately. These images contained thousands of galaxies, some faint, some bright, some so distant their light had been traveling toward us for more than 13 billion years. At first, the analysis focused on mapping galaxy shapes and estimating their ages. Researchers expected most early galaxies to look small and irregular, primitive, still gathering material, and many of them did look like that. But scattered among those tiny early systems were a few objects that stood out. They were brighter than expected. Not dramatically brighter, but enough to catch attention. Think of looking across a distant city skyline at night. Most windows glow softly. Then one building shines far brighter than the others. You notice it immediately. That is how some of these galaxies appeared in Webb's observations. Astronomers began asking a simple question. Why are these galaxies so bright? Brightness in a galaxy usually comes from two main sources. The first is star formation. When large clouds of gas collapse to form new stars, the process releases enormous amounts of light. Young stars burn hot and blue, creating bright regions within galaxies. The second source is far more dramatic. A feeding black hole. When gas and dust spiral toward a black hole, they do not fall straight in. Instead, they form a rotating disk. This disk becomes extremely hot, hot enough to glow across enormous distances, sometimes brighter than the entire galaxy around it. Astronomers call these objects active galactic nuclei, or AGN. The center of the galaxy shines like a cosmic furnace. So when Webb revealed unusually bright galactic cores, researchers began looking for signs that might indicate one of these feeding black holes. At first, the idea seemed unlikely. Remember where these galaxies existed in time. The universe was still very young. Some of these galaxies appeared only 500 to 700 million years after the Big Bang. In cosmic terms, that is extremely early. Black holes normally begin as the collapsed remnants of massive stars. Those stellar black holes might start with masses 10 or 20 times that of our Sunday. From there, they slowly grow. They gather gas. They merge with other black holes. Over hundreds of millions of years, they can become enormous. But that process takes time. A lot of time, which meant the early universe should not yet contain black holes. Millions of times the mass of the Sunday. The timeline simply seemed too short. Still, the brightness in Webb's images demanded investigation. Scientists turned to spectroscopy. This technique spreads light into its component wavelengths, like a prism separating sunlight into colors. Each chemical element produces a unique pattern in this spectrum. More importantly, certain physical processes leave recognizable signatures. Gas heated by intense gravity produces very specific spectral lines. Matter spiraling toward a black hole leaves a distinctive pattern, and when astronomers examined the spectral fingerprints of those bright galactic centers, the signals began matching that pattern. Pause for a moment, because this is the moment the mystery started to form. At first, researchers thought the signals might come from bursts of star formation. Young galaxies often produce intense regions of new stars, but star formation leaves a different signature. Broader emission, different temperature patterns. The Webb spectra did not match that. Instead, they looked much closer to the patterns seen in active galactic nuclei, the same type of signals astronomers detect around supermassive black holes in the modern universe. That was unexpected, but unexpected results happen in astronomy. Sometimes instruments misinterpret light. Sometimes dust clouds distort observations. Sometimes distant objects overlap in images. So scientists did what scientists always do. They checked the numbers again. They ran the calculations through different models. They examined the images from multiple instruments aboard Webb. The results remained consistent. Several early galaxies appeared to contain extremely energetic cores that looked suspiciously like black holes feeding on surrounding gas. But if that interpretation was correct, a much bigger problem appeared, because energy output can reveal the size of the black hole producing it. The brighter the emission from the accretion disk, the larger the black hole must be. And when astronomers estimated the masses required to produce those signals, the numbers became uncomfortable. Some of those early black holes appeared to weigh millions of times the mass of the Sunday. Imagine discovering a skyscraper standing in a town that was only supposed to have small houses. That is roughly what this observation suggested. According to standard growth models, even a rapidly feeding black hole should need hundreds of millions of years to reach that size. Yet these galaxies existed during the universe's first billion years. There simply should not have been enough time. Researchers began asking another question. What if the brightness was coming from something else? Perhaps a rare type of star cluster? Perhaps a burst of supernova explosions? Perhaps an unusual form of stellar activity we do not yet fully understand. Each possibility was explored, but many of them failed to match the spectral fingerprints Webb had detected. The more the data was analyzed, the more the same possibility kept returning. Black holes, large ones, much earlier than expected. And then one particular observation appeared. An object so distant that its light had been traveling toward us for more than 13 billion years. Yet the energy coming from its center suggested something extraordinary. A black hole already massive, already feeding, already influencing the galaxy around it. Astronomers stared at those numbers for a long time, because if the measurements were correct, the object existed when the universe was only about 570 million years old. That is not much time in cosmic terms. Picture building an entire city in a single afternoon. That is how fast this black hole seemed to have formed, and if that interpretation was correct, something in our understanding of cosmic growth was missing. The early universe might have been far more efficient at building massive objects than anyone predicted, or black holes might have had a completely different origin. But either way, the discovery pointed to a disturbing conclusion. Somewhere in the early universe, enormous black holes appeared far earlier than our theories allow, and the deeper astronomers looked into the data, the more impossible the numbers began to seem. Astronomers have discovered many strange objects over the past century. Pulsars that spin hundreds of times per second, stars so dense a teaspoon would weigh billions of tons, galaxies colliding in slow motion across millions of years. The universe is full of surprises, but occasionally an observation appears that does something more unsettling. It does not just surprise scientists, it challenges the timeline itself. That is what began happening as researchers studied one particular object detected by the James Webb Space Telescope. At first, it looked like another distant galaxy, a faint patch of light buried deep inside Webb's deep field images. But inside that faint galaxy, the center was glowing far brighter than expected, not with the scattered brightness of new stars, with something more focused, more intense. Picture standing on a dark hillside and looking toward a distant city. Most of the lights blur together, but one building stands out, a brilliant beam from a single tower. That is roughly how this galaxy appeared. Its core was shining like a concentrated furnace. Astronomers began analyzing the data more carefully. They measured the galaxy's distance first, because distance determines age. The farther away the galaxy, the older the light. And the measurements showed something remarkable. The light had traveled more than 13 billion years before reaching Earth, which meant the galaxy existed when the universe itself was only about 570 million years old. Pause for a moment and imagine that. The universe today is around 13.8 billion years old. This object appeared when cosmic history had barely begun. At that time, galaxies should still have been forming their first stars. Structures were supposed to be small and unstable, yet something enormous seemed to be active at the center of this galaxy. The brightness alone suggested powerful gravitational activity, so astronomers turned again to spectroscopy. Breaking the light into detailed wavelengths allowed them to examine the motion of gas near the galaxy's core. Gas moving near a black hole travels extremely fast, sometimes thousands of kilometers per second. Those speeds leave distinctive signatures in the spectral lines, and when researchers measured those signatures, the results were unmistakable. The gas was moving incredibly fast, fast enough to suggest the presence of a massive gravitational object, a black hole. But how massive? That question required careful modeling. Scientists compared the energy output of the glowing disk around the object with known examples of active black holes. From that comparison, they could estimate the mass required to produce the observed brightness. When the first estimate appeared, many researchers assumed it had to be wrong. The numbers suggested a black hole roughly 10 million times the mass of the Sun, inside a galaxy that existed when the universe was still extremely young. That should not have been possible. To understand why, imagine building a mountain out of grains of sand. You start with a small pile, then you add more grains one by one. Eventually, the pile grows large, but the process takes time. Black holes grow in a similar way. They begin small and slowly gather mass. Gas falls inward, stars drift too close, other black holes merge. Over billions of years, the object grows, but the growth rate has limits. There is a natural barrier known as the Eddington limit. When matter falls toward a black hole, the gas becomes extremely hot and bright. The radiation from that hot gas pushes outward against incoming material. like wind pushing against falling snow. If the radiation becomes too strong, it actually slows the rate at which matter can fall inward. This creates a speed limit for black hole growth. Even under ideal conditions, it takes hundreds of millions of years for a small stellar black hole to grow into a supermassive one. Now remember the age of this galaxy, only about 570 million years after the Big Bang, and the black hole inside it already seemed to weigh 10 million suns. Even if a stellar black hole had formed immediately when the first stars exploded, the timeline still did not quite work. There simply had not been enough time for it to grow that large. Astronomers ran the calculations again. They checked the redshift measurements. They tested alternative models. Could the brightness come from intense star formation? Perhaps thousands of massive stars exploding in rapid succession? But the spectral patterns did not match that scenario. The energy was too concentrated, too stable. Another possibility emerged. Maybe the black hole started larger. Instead of forming from a single star, perhaps it formed directly from the collapse of a huge gas cloud. That idea had existed in theoretical models for years, but it was rarely observed. Still, even that explanation struggled to produce objects of this size so early in cosmic history. The discovery began spreading through the astronomical community. Researchers discussed it in conference calls. Preliminary papers began circulating. More teams examined Webb's data independently, and something unsettling started to appear. This object was not alone. Several early galaxies seemed to contain black holes far larger than expected. The pattern suggested this was not a rare accident. It might be something more common in the early universe. Think about what that means. If massive black holes existed within the universe's first few 100 million years, then our models of cosmic evolution may be incomplete. Galaxies might have formed faster than expected. Black holes might have grown faster than allowed. Or entirely new processes may have shaped the earliest structures in the cosmos. Picture trying to reconstruct the history of a city only to discover skyscrapers already standing in its earliest photographs. Something in the timeline would have to change. And that is exactly the situation astronomers began facing. Because if these measurements were correct, the early universe was not a quiet place slowly assembling its first structures. It was building enormous objects almost immediately. But that realization led to another question. If a black hole of 10 million solar masses already existed so early, how did it begin? Because the standard model of black hole formation was starting to look increasingly fragile, and scientists now had to confront a deeper possibility. Maybe the way black holes form in the early universe is very different from what we have assumed. Before the discovery of these early objects, astronomers believed they understood the basic story of how supermassive black holes grow. The explanation was simple, slow, gradual, almost patient. The story begins with a star, not a small one like our Sun, but a massive star many times larger. These stars burn their fuel quickly. Their cores become incredibly hot and dense as nuclear reactions push outward against gravity. But eventually, the fuel runs out. When that happens, the balance collapses. Gravity wins. The star's core falls inward with incredible force, crushing matter together until it becomes something entirely different. A black hole is born. Most stellar black holes formed this way weigh somewhere between 5 and 50 times the mass of the Sunday. Small by cosmic standards, picture a seed, tiny compared to the forest it might one day grow into. Now imagine that seed placed in the center of a galaxy. Gas clouds drift through space. Stars move along their orbits. Every so often, some of that material passes close enough to the black hole to be captured. Once trapped by gravity, the material begins spiraling inward. It does not fall straight down. Instead, it forms a glowing whirlpool called an accretion disk. Picture water circling a drain. The motion becomes faster and faster. The closer it moves toward the center, gas inside this disk heats up dramatically. Temperatures climb into millions of degrees. The disk shines brilliantly across space, sometimes brighter than the galaxy surrounding it. While this happens, the black hole slowly grows. Matter crosses the invisible boundary known as the event horizon. and once it passes that line, it can never escape again. The black hole becomes heavier, a little at a time, over enormous spans of time. Imagine a snowball rolling down a hill during a long winter storm. At first, the snowball is small, but as it rolls, it gathers more snow. It grows. That is roughly how astronomers believed supermassive black holes formed. The process simply takes a very long time, hundreds of millions of years, sometimes billions. And there is another important limit. The brightness of the accretion disk creates pressure. Light itself pushes outward. If too much gas tries to fall toward the black hole at once, the radiation from the disk pushes it away, like wind blowing against falling snow. This creates a natural speed limit for growth. Astronomers call this the Eddington limit. It acts as a regulator. Black holes cannot simply swallow unlimited amounts of matter instantly. They grow at a steady pace, slow enough that even after billions of years, only the largest galaxies host the most massive black holes. Our own galaxy provides a good example. At the center of the Milky Way lies Sagittarius A*, a black hole roughly 4 million times the mass of the Sunday. It took billions of years to reach that size. Other galaxies contain even larger ones. Some weigh billions of solar masses, but again, they exist in galaxies that have had the entire history of the universe to evolve. Now picture the timeline scientists expected for the early universe. The first stars appear around 100 to 200 million years after the Big Bang. Some of those stars explode as supernovae. Their cores collapse into small black holes. Those black holes begin slowly gathering material. Over hundreds of millions of years, they grow larger. Over time, they merge with other black holes. Gradually, the first supermassive black holes appear. This process should take a very long time, which is why astronomers believed massive black holes would only appear much later in cosmic history. But the objects Webb was revealing did not follow that script. They seemed to skip several steps. Instead of small seeds slowly growing, the observations suggested something very different. Massive black holes already existed when the universe was still young. Picture planting a tree seed and returning a few weeks later to find a full-grown oak. That is roughly how strange these discoveries appeared. Even under ideal conditions, the numbers did not line up. Researchers tried pushing the growth models to their extreme limits. What if a black hole grew continuously at the maximum allowed rate? What if it never stopped feeding? What if it began growing the moment the first stars exploded? Even under those generous assumptions, the growth still seemed too slow. A stellar black hole starting at 10 solar masses would struggle to reach 10 million solar masses in only a few 100 million years. The math resisted the idea, but the observations were becoming harder to ignore. Several early galaxies seemed to host black holes far larger than expected. Astronomers began asking a difficult question. What if the seeds themselves were larger? Instead of beginning with small stellar black holes, perhaps the first black holes formed in a completely different way. Picture skipping the seed stage entirely. Imagine something starting already enormous. That idea had been proposed before, but until recently, there had been little evidence supporting it. Now, Webb's observations were forcing scientists to reconsider that possibility, because if the black holes began much larger, the timeline might finally make sense. And that leads to a fascinating concept known as direct collapse, a theory suggesting that some of the first black holes may have formed not from dying stars, but from the collapse of entire clouds of gas. If that process occurred in the early universe, it could create black holes thousands or even millions of times heavier than a normal stellar remnant, large enough to grow into supermassive giants far faster than traditional models allow. At first glance, the idea sounds dramatic, but the early universe may have provided exactly the right conditions for it. And if that theory turns out to be correct, it would mean something remarkable. Some of the largest black holes in the universe might have been born already enormous. When the numbers from the early Webb observations refused to cooperate, astronomers began revisiting an idea that had lived quietly in theoretical papers for years. It was called direct collapse. The concept is simple to describe, but the consequences are enormous. Instead of forming from a dying star, a black hole might form when an entire cloud of gas collapses directly into one. No star first, no explosion, just gravity pulling a massive cloud inward until it becomes something incredibly dense. To understand why this idea matters, imagine two different ways of building a mountain. The first way is slow. You carry rocks one by one. You stack them carefully. Over time, the pile grows taller. That is similar to the standard model of black hole growth. Small seeds gradually becoming larger. But the second way is very different. Instead of stacking stones, the entire hillside suddenly slides downward in a massive landslide. Instant mountain. That is roughly what direct collapse proposes. In the early universe, enormous clouds of gas may have collapsed straight into black holes, thousands or even millions of times the mass of the Sunday. If that happened, the timeline problem begins to look very different, because now the starting point is much larger. Pause for a moment and think about what that means. Instead of beginning with a 10 solar mass black hole, the universe might have created objects weighing 100,000 suns or more. From there, growth becomes much easier. The black hole only needs to increase its mass by a factor of 100 to reach 10 million solar masses. That is still impressive, but it becomes far more achievable within a few 100 million years. So the question becomes simple. Could the early universe actually produce these giant collapsing gas clouds? At first glance, the idea seems difficult. Gas clouds in galaxies usually form stars before they can collapse further. Stars ignite quickly once gas becomes dense enough, and once stars appear, they disrupt the cloud. Radiation and stellar winds push gas outward. Supernova explosions scatter material in every direction. The cloud breaks apart. Direct collapse requires something unusual. A gas cloud must remain hot and stable long enough to avoid forming stars. Only then can it continue collapsing inward. Scientists began examining the conditions of the early universe carefully, and they realized something interesting. The very first galaxies may have contained enormous amounts of pristine hydrogen gas, almost no heavy elements. Those early environments behaved differently from modern galaxies. Heavy elements help gas cool quickly. Cooling allows clouds to fragment into smaller pieces that form stars. But without those elements, gas remains warmer and smoother. Instead of breaking apart into many small clumps, the cloud might stay intact. Imagine pouring thick honey onto a surface. It flows slowly and remains connected. Now imagine pouring water. It breaks into droplets almost immediately. Early cosmic gas behaved more like honey. Under certain conditions, that gas could collapse into a single massive structure. Gravity would pull inward, pressure would rise, temperatures would increase, and eventually the entire cloud could collapse into a massive black hole seed. This idea excited many theorists, but for years there was little observational evidence to support it. Direct collapse black holes remained hypothetical. Then the James Webb Space Telescope arrived, and suddenly the early universe started revealing objects that looked suspiciously like the outcome of such a process. Some distant galaxies appeared to host black holes already extremely large for their age, too large to grow from ordinary stellar remnants, yet perfectly reasonable if the starting seed was already enormous. Picture again that mountain example. If the mountain begins as a landslide instead of a small pile of rocks, its size makes much more sense. Still, the direct collapse hypothesis faces its own challenges. Creating those massive gas clouds requires very specific conditions. The cloud must avoid fragmentation. It must avoid star formation long enough to collapse. It must remain stable while gravity pulls it inward. Some researchers believe intense radiation from nearby galaxies could play a role. Strong ultraviolet light might suppress star formation inside certain clouds. That radiation would prevent the gas from cooling too quickly. The cloud would remain warm and smooth. Gravity could continue pulling inward, eventually forming a massive black hole seed. Think of it like keeping a pot of water just warm enough so it never freezes into smaller pieces. The conditions must be carefully balanced, but the early universe may have provided those conditions more often than we once thought, and that possibility raises an intriguing idea. What if many of the first galaxies formed around black holes, rather than the other way around? Traditionally, astronomers assumed galaxies formed first, then black holes appeared at their centers. But if direct collapse occurred early enough, massive black holes might have existed before fully formed galaxies. Their gravity could help gather surrounding gas. Stars would form later around them. The order of cosmic construction might be reversed. That is a radical thought, but some of Webb's observations are beginning to hint in that direction. And if that idea proves correct, it means the early universe may have built its most powerful objects far earlier than we ever imagined. Still, even direct collapse does not solve every mystery, because some black holes Webb has detected appear even larger than direct collapse models predict, which means the story might be even more complicated. And that leads to another surprising observation. It is not just black holes that seem to be growing too fast. Entire galaxies may have formed far earlier than expected. As astronomers continued studying the early observations from the James Webb Space Telescope, another pattern began to appear. At first, the focus had been on black holes. They were the most dramatic part of the mystery. But when researchers looked closer at the galaxies themselves, something equally strange emerged. Many of them seemed too mature. Pause for a moment and picture what scientists expected to see. The early universe should have looked like a rough construction zone. Small galaxies, irregular shapes, clouds of gas still collapsing into stars. Imagine looking at the earliest villages forming across a wide landscape. Simple structure, not cities yet, but Webb's images sometimes showed something different. Some galaxies appeared surprisingly bright and massive. Their light suggested they already contained enormous numbers of stars. In some cases, hundreds of millions, or even billions. That alone raised questions, because stars do not form instantly. Gas clouds collapse slowly. Gravity pulls matter inward over time. Star formation spreads through galaxies gradually. Building large stellar populations should require hundreds of millions of years. Yet here were galaxies existing only 500 to 700 million years after the Big Bang that already seemed well populated with stars. Picture walking into a forest that should have just begun growing. Instead of saplings, you find towering trees. Something about the growth rate appears wrong. Astronomers began calculating how quickly these galaxies would need to form stars to reach the brightness Webb was observing. The numbers were astonishing. Some galaxies appeared to be producing stars 10 times faster than models predicted for the early universe. Gas was turning into stars at an incredible pace. If these measurements were correct, early galaxies may have built their stellar populations much more rapidly than expected. Now consider what that means for black holes. Galaxies and black holes are deeply connected. In nearly every large galaxy we observe today, the mass of the central black hole correlates closely with the mass of the galaxy's stars. When galaxies grow, their central black holes often grow as well. It is almost as if the two evolve together. Think of them like two dancers moving across the same stage. Their motions are linked, so if early galaxies were forming stars unusually fast, their central black holes might also have had access to enormous amounts of gas, fuel, the raw material needed for rapid growth. But that introduces another puzzle. Even if galaxies formed stars quickly, feeding a black hole fast enough to reach millions of solar masses still runs into the Eddington limit. Remember that limit. Radiation from the accretion disk pushes outward. Too much gas, falling inward, creates pressure that slows the process. Imagine trying to pour sand into a funnel. At first, it flows easily, but if you pour too quickly, the funnel clogs. Black holes have a similar bottleneck. Gas cannot fall inward infinitely fast. Yet Webb's observations suggested black holes might have grown extremely rapidly. Somehow, the early universe may have bypassed those limits. One possibility is that the environment around early black holes was far denser than in modern galaxies. Gas clouds were thicker, more chaotic, matter constantly colliding and falling inward. Under such conditions, black holes might feed almost continuously. Imagine standing beneath a waterfall instead of catching occasional rain. The flow becomes constant. Another factor may involve galaxy mergers. In the young universe, galaxies collided far more frequently. When galaxies merge, enormous streams of gas fall toward their centers. Those streams can feed central black holes aggressively. Picture two rivers joining together and rushing into a single basin. The combined flow becomes powerful. If early galaxies merged often enough, their central black holes might have received steady supplies of fuel. That would accelerate their growth. Still, even aggressive feeding has limits. The most extreme Webb observations suggest some black holes reached massive sizes very quickly, which means either the feeding process was far more efficient than we understand, or the starting seeds were already large. Now combine that with the galaxy growth problem. If galaxies themselves formed stars unusually quickly, and if their central black holes were feeding at extreme rates, the early universe may have been far more dynamic than our models predicted. Instead of a slow cosmic dawn, the first billion years may have been an era of rapid construction, structures forming everywhere, stars igniting in bursts, black holes growing rapidly. Picture a landscape where entire cities appear almost overnight. That might be closer to what the early universe actually looked like, but scientists remain cautious. Brightness measurements can sometimes be misleading. Dust can hide stars. Galaxies can appear larger if multiple objects overlap along our line of sight. Astronomers continue analyzing Webb's data carefully. More observations will help clarify the picture. Still, the pattern keeps appearing. Some early galaxies look larger and more developed than expected, and many of them appear to host active black holes at their centers, which means two things may be happening at once. Galaxies growing fast, black holes growing fast, and when those two processes combine, the cosmic timeline begins to shift. But even if galaxies provided enormous amounts of fuel, one critical problem remains, because feeding a black hole is not just about having gas nearby. The gas must also fall inward efficiently, and that process may involve something even more mysterious about the early universe. By the time astronomers reached this stage of the investigation, the mystery had narrowed to a single question. How did these black holes grow so quickly? The early universe clearly contained enormous amounts of gas. Galaxies were rich with hydrogen and helium. Stars were forming rapidly. Fuel was not the issue. The real problem was how that fuel reached the black hole, because feeding a black hole is not as simple as dropping matter straight into a hole in space. Gravity pulls gas inward, yes, but the universe is rarely that neat. Gas clouds move with momentum. They spin, they collide, they swirl around galaxies in complex orbits. That motion creates a barrier. Picture trying to pour water directly into the center of a spinning carousel. The water does not fall straight down. It spreads outward. In galaxies, the same thing happens. Gas tends to orbit the center instead of falling directly inward. To reach the black hole, that gas must lose energy and angular momentum. Only then can it spiral inward through an accretion disk. This process usually takes time, sometimes a lot of time, and even once gas reaches the disk, another obstacle appears: heat. As matter falls closer to the black hole, it accelerates dramatically. The gas compresses and heats up to extreme temperatures, millions of degrees. At those temperatures, the gas begins emitting intense radiation. That radiation pushes outward against incoming material. Imagine standing in front of a powerful wind while trying to throw sand forward. The wind blows it back toward you. In black hole physics, this balance between gravity pulling inward and radiation pushing outward defines the Eddington limit. It is essentially the speed limit for how fast a black hole can grow. If a black hole tries to swallow matter faster than this limit allows, the radiation pressure pushes surrounding gas away. The feeding slows down. Think of it like traffic entering a tunnel. Cars can only move through the tunnel so quickly. Even if thousands of cars arrive at once, the tunnel limits the flow. For decades, Astronomers assumed this limit controlled black hole growth across the universe. It explained why supermassive black holes required billions of years to reach their enormous sizes. But the early universe may have been different. Some researchers now suspect that the Eddington limit might not always apply as strictly as once believed. Picture again that tunnel. Now imagine the tunnel suddenly expanding. More lanes open, cars move faster. Under certain extreme conditions, black holes might temporarily exceed the usual growth limit. This process is called Super-Eddington accretion. Instead of feeding slowly, the black hole consumes matter at an accelerated rate. Gas piles into the accretion disk faster than radiation can push it away. Dense streams of material continue falling inward. The disk becomes chaotic, thick, violent, but the black hole grows quickly, much faster than traditional models predicted. Scientists have observed hints of this behavior in some modern galaxies, but the early universe may have allowed it to happen more often. Remember how dense those early galaxies were. Gas everywhere, collisions common, galaxies merging frequently. Under those conditions, gas might have been funneled toward the center in massive streams. Picture rivers pouring into a whirlpool. The whirlpool cannot reject all the water. Some of it must fall inward. Another possibility involves the structure of the accretion disk itself. In many models, the disk is thin and bright. Radiation escapes easily. That radiation pushes gas away. But if the disk becomes thick and turbulent, radiation can become trapped inside it. Instead of escaping outward, the light gets dragged inward along with the falling gas. Imagine fog trapped inside a swirling storm. The light cannot escape easily. Gravity wins. Under those conditions, black holes might feed far faster than previously believed. And if that happened in the early universe, it could help explain Webb's observations. Large black holes forming quickly, growing rapidly in dense young galaxies. Still, even this explanation leaves questions, because some of the black holes detected by Webb appear extremely massive for their age. Even faster growth might not fully explain them, which leads to an even stranger possibility. Perhaps some of the first black holes did not grow from stars at all. Perhaps they existed before galaxies, before stars, maybe even before the first cosmic structures fully formed. That idea sounds almost impossible, but it connects to one of the oldest and most mysterious theories in cosmology, the idea of primordial black holes, objects that may have formed in the earliest moments of the universe itself. If those objects existed, they could have acted as the seeds around which galaxies later formed. But if that theory is correct, it means some black holes may be almost as old as the universe itself, and that possibility opens an entirely new chapter in the story of cosmic origins. By now, the mystery had pushed scientists into unfamiliar territory. The early universe seemed to contain black holes far larger than expected. Galaxies appeared to form quickly. Matter gathered faster than many models predicted. So researchers began asking a deeper question. What if some black holes did not begin with stars at all? Instead, what if they were born during the earliest moments of the universe itself? This idea leads to something called primordial black holes. Pause for a moment and picture the universe immediately after the Big Bang. Everything was compressed into an extremely dense state. Energy filled every region of space. Matter and radiation moved through a rapidly expanding environment that was anything but smooth. Tiny fluctuations existed everywhere, small regions slightly denser than their surroundings. Under the right conditions, those dense regions could collapse under their own gravity. And if the collapse was strong enough, a black hole could form directly from that early cosmic material. No stars required, no galaxies required, just gravity acting on density fluctuations in the newborn universe. Imagine the surface of the ocean during a violent storm. Most waves rise and fall normally, but occasionally one wave becomes unusually tall. If gravity pulls it down hard enough, it crashes with enormous force. The early universe may have behaved in a similar way. Most regions expanded smoothly. but rare pockets of matter might have collapsed inward. Those collapses could have produced black holes very early in cosmic history, perhaps within seconds or minutes after the Big Bang. If that happened, the universe might contain black holes far older than any star. These primordial black holes would start small. Some might weigh as much as a mountain. Others might reach the mass of an asteroid. But under certain conditions, larger ones could form as well. And here is where things become interesting. If primordial black holes existed, they would have had an enormous head start. Instead of forming hundreds of millions of years later from dying stars, they would already be present when the first gas clouds began gathering into galaxies. Picture building a city around an ancient stone tower that was already standing when construction began. That tower would shape everything around it. Gas drifting through early space would feel the gravity of those black holes. Matter would begin gathering near them. Stars might ignite in orbit around them. Over time, entire galaxies could form around these ancient gravitational anchors. It is a fascinating idea, but also controversial. For decades, primordial black holes remained mostly theoretical. Astronomers searched for signs of them in different ways. Some looked for gravitational lensing effects, small black holes bending light from distant stars. Others searched for radiation signals that might appear if tiny primordial black holes evaporated through a process called Hawking radiation. So far, the evidence has been uncertain, but the new discoveries from the James Webb Space Telescope have revived interest in this idea, because primordial black holes could solve several puzzles at once. First, they would explain why some black holes appear extremely early in cosmic history. They would already exist long before stars began producing stellar black holes. Second, they could provide the large seeds needed to grow supermassive black holes quickly. A primordial black hole, starting with thousands or millions of solar masses, would not need much time to become enormous. Third, they might even connect to another major mystery in cosmology, dark matter. Some scientists have proposed that primordial black holes might make up part of the invisible mass that fills the universe. Dark matter is thought to account for roughly 85% of all matter in the cosmos, yet we still do not know what it is made of. If some of that dark matter consists of ancient black holes formed in the early universe, it could explain certain gravitational effects observed across galaxies. Still, this idea remains speculative. Most cosmological models do not require primordial black holes to exist, and many observations place limits on how many of them could be present. But the strange discoveries coming from Webb are encouraging scientists to revisit possibilities that once seemed unlikely. Because when observations do not match theory, scientists must expand the list of explanations. Think of it like solving a puzzle, where several pieces no longer fit the picture. You can force the pieces into place, or you can step back and ask whether the picture itself might be incomplete. Right now, astronomers are doing exactly that. They are re-examining the early universe with fresh eyes, testing ideas that once seemed too unusual. Because the deeper we look into cosmic history, the more the universe seems to resist simple explanations. Black holes appearing earlier than expected, galaxies forming faster than predicted, and perhaps ancient objects that existed long before the first stars ignited. But even if primordial black holes turn out to be rare, one conclusion is becoming difficult to ignore. The early universe may have been far more active than we once believed. Structures forming quickly, gravity shaping matter with incredible speed, and enormous objects appearing long before our models predicted, which leads to an unsettling possibility. If the timeline of black hole formation is shifting, then the entire timeline of cosmic evolution may need to change as well. For most of modern astronomy, the early universe followed a simple storyline. It began slowly. After the Big Bang, the cosmos expanded and cooled. Gas drifted through space. Gravity gradually gathered that gas into small clumps. Stars ignited, galaxies slowly assembled, and only after long periods of growth did the largest cosmic structures appear. That picture guided decades of research, but the observations coming from the James Webb Space Telescope are beginning to challenge that calm narrative. Because when scientists look at galaxies less than 1 billion years after the Big Bang, they are sometimes seeing objects that appear far more developed than expected. Some contain enormous numbers of stars. Others host active black holes already millions of times the mass of the Sunday. That combination raises an uncomfortable question. What if the early universe did not develop slowly? What if cosmic structure appeared far more quickly than we believed? Picture planting seeds in a field and expecting small sprouts to appear after weeks. Instead, you return to find entire forests already growing. That is roughly the situation astronomers are facing. The timeline of cosmic growth may need revision. To understand why this matters, imagine building a timeline of human history. You expect early villages first, then towns, then cities, finally large civilizations. But what if archaeologists suddenly discovered massive cities already standing at the very beginning of the timeline? The entire sequence of development would need to be reconsidered. Something must have accelerated the process. That is exactly the puzzle now appearing in cosmology. Because galaxies and black holes are not isolated objects, they influence each other. Stars produce heavy elements. Black holes shape gas flows. Galaxies merge and interact. Everything evolves together. So if one part of the system develops faster than expected, the entire timeline shifts. Astronomers are now examining several possibilities. One idea is that star formation was extremely efficient in the early universe. Gas may have collapsed into stars much faster than modern galaxies allow. Early galaxies contained enormous reservoirs of hydrogen gas. With fewer heavy elements to cool and fragment the gas clouds, star formation might have proceeded differently. Instead of slowly forming clusters of stars, some early clouds might have collapsed rapidly, producing bursts of stellar activity. Picture a field catching fire all at once, rather than slowly lighting one patch at a time. That would produce bright galaxies very quickly. Another possibility involves the density of the early universe itself. During the first billion years, galaxies were packed much closer together than they are today. Collisions and mergers were far more common. Each collision could funnel huge streams of gas toward galactic centers. Those streams could ignite star formation and feed central black holes simultaneously. Imagine rivers merging together into a single basin. The combined flow becomes powerful. Under such conditions, galaxies might grow rapidly. Black holes might feed continuously. Entire structures could evolve faster than expected. But even these explanations might not tell the whole story. Some Webb observations suggest galaxies may have formed earlier than predicted by certain cosmological simulations. If that is true, it might mean the distribution of matter in the early universe was slightly different than current models assume. Even small differences in the initial density fluctuations after the Big Bang could change how quickly structures formed. Think of baking bread. If the yeast activates faster than expected, the dough rises much more quickly. The same ingredients produce a different outcome simply because the process begins earlier. Cosmic structure formation may work in a similar way. Tiny variations in early density could dramatically change how galaxies grow. Scientists are now running new computer simulations using updated data from Webb. These simulations attempt to recreate the universe from its earliest moments, adjusting different parameters to see which conditions produce galaxies similar to those we observe. Some models now suggest that massive galaxies could indeed form earlier than previously believed, especially if gas cooling and star formation behave differently under early cosmic conditions. But the research is ongoing. Astronomers remain cautious. One telescope cannot rewrite an entire cosmological framework overnight. More observations will be needed, more galaxies studied, more black holes measured. Still, the evidence continues to build. The early universe might not have been a quiet place, slowly assembling its first structures. It may have been an era of rapid growth, stars igniting everywhere, galaxies forming quickly, black holes appearing sooner than expected. And if that is true, it forces scientists to rethink one of the most fundamental questions in cosmology. How did matter organize itself so efficiently during the universe's first billion years? Because gravity alone may not explain everything. Another invisible force may have played a much larger role than we once imagined. A force we cannot see directly, but one that shapes the structure of the entire universe. Dark matter. And if dark matter behaved differently in the early cosmos, it might hold the key to how these enormous objects formed so quickly. Up to this point, most of the story has focused on things we can see. Stars, galaxies, black holes glowing as they feed. But the truth is, most of the universe is invisible. In fact, everything made of normal matter, every planet, every star, every galaxy, accounts for only a small fraction of the cosmos, roughly 5%. The rest is something else. About 27% of the universe appears to be made of something scientists call dark matter. We cannot see it. It does not shine. It does not reflect light. Yet its gravity shapes the structure of the universe on enormous scales. Pause for a moment and imagine a city at night during a power outage. The buildings are still there. The streets still exist. But without lights, the city becomes invisible. Dark matter is somewhat like that. It forms a hidden framework that holds galaxies together. Astronomers first suspected its existence when they noticed something strange about how galaxies rotate. Stars far from the center of galaxies move much faster than expected. If only visible matter were present, those stars should fly outward into space. But they remain bound to their galaxies. Something unseen must be providing additional gravity. That unseen mass became known as dark matter. Over time, scientists realized dark matter does more than hold galaxies together. It also helps build them. In modern cosmology, dark matter acts like a cosmic scaffold. Imagine constructing a city by first laying down a network of steel beams. Once the framework exists, buildings can grow around it. Dark matter provides a similar structure for galaxies. After the Big Bang, tiny fluctuations in the density of dark matter began pulling surrounding gas toward them. Those gravitational wells acted as seeds where galaxies eventually formed. Normal matter, hydrogen, and helium gas fell into those invisible halos. Stars ignited, galaxies emerged. That basic idea has guided cosmological simulations for decades. But Webb's discoveries are raising new questions about how those dark matter halos behaved in the early universe. If galaxies appeared earlier than expected, it may mean dark matter structures formed faster than predicted. Imagine a landscape where the scaffolding for cities appeared almost instantly. Construction could begin much sooner. Galaxies might grow quickly around those hidden frameworks. Black holes might receive large supplies of gas from the start. Another possibility involves the density of early dark matter halos. If some halos were unusually massive very early in cosmic history, they could have gathered enormous amounts of gas. That gas would collapse toward the center, forming stars and possibly feeding massive black hole seeds. Picture a deep valley collecting rainwater during a storm. The deeper the valley, the more water it gathers. Dark matter halos act like those valleys. Their gravity pulls matter inward, and the deeper the gravitational well, the more material it can collect. Some researchers now believe the earliest galaxies Webb has detected may sit inside exceptionally massive dark matter halos. If that is true, the presence of large black holes in those galaxies becomes easier to understand. More gas, more star formation, more fuel for black hole growth. Still, dark matter remains mysterious. We do not yet know what it is made of. Several candidates have been proposed over the years. Weakly interacting particles, exotic forms of matter, even tiny black holes. Experiments around the world continue searching for evidence. Deep underground detectors, particle accelerators, space-based observations. So far, the nature of dark matter remains one of the greatest unsolved problems in physics. But its gravitational influence is undeniable. Without dark matter, galaxies like the Milky Way could not exist. Without dark matter, the large-scale structure of the universe would look completely different. And without dark matter halos forming early in cosmic history, galaxies might not have gathered the material needed to grow quickly, which means dark matter may play an indirect role in the mystery Webb is uncovering. It may not create black holes directly, but it may provide the gravitational framework that allows galaxies and their central black holes to grow rapidly. Think of dark matter as the stage upon which the cosmic story unfolds. Stars are the actors, galaxies are the cities, black holes are the powerful engines at their centers. But the stage itself determines how the story begins. If that stage formed earlier than expected, the entire sequence of cosmic evolution could shift forward in time, and that possibility leads to the next question scientists are asking. What else might the James Webb Space Telescope reveal as it continues exploring the early universe? Because the observations so far may only be the beginning, Webb has only just started looking, and every new dataset has the potential to uncover something even stranger. The discoveries we have discussed so far came from Webb's first observations. That detail matters, because the telescope has only just begun its work. Think about that for a moment. Humanity spent more than 20 years designing and building this machine. Engineers tested every mirror, every instrument, every delicate unfolding mechanism. Then the telescope traveled nearly 1 million miles from Earth, and only recently did it begin sending back its first real views of the deep universe. What we are seeing now is the beginning of a much longer investigation. Imagine opening the first page of a very large book. The early chapters already contain surprises, but the rest of the story has not yet been read. The James Webb Space Telescope is capable of observing objects even farther away than the ones we have discussed so far. That means it may detect galaxies that existed just a few 100 million years after the Big Bang, perhaps even earlier. And if the patterns we are seeing continue, astronomers may discover something remarkable. More galaxies forming earlier than expected. More massive black holes appearing sooner than our models predict. Each new observation adds another piece to the cosmic puzzle, but Webb does more than take pictures. Its instruments analyze light in extraordinary detail. They measure chemical signatures, revealing what elements exist inside distant galaxies. They detect the motion of gas clouds. They estimate the masses of black holes and stars. In some cases, Webb can even examine the atmospheres of distant planets orbiting other stars. All of this information helps scientists reconstruct the history of the universe. Picture an archaeologist slowly uncovering an ancient city buried beneath sand. Every brush of dust reveals another detail. A wall, a doorway, a road connecting two buildings. Eventually, the entire city becomes visible. Webb is performing a similar task across cosmic time. But there is another powerful tool helping astronomers interpret Webb's discoveries: computer simulations. Modern cosmology relies heavily on simulations that recreate the universe from its earliest moments. Scientists feed enormous amounts of data into supercomputers. They start with the known conditions of the early universe: temperature, density, expansion rate. Then they allow gravity and physics to evolve the system forward in time. Galaxies appear, stars ignite, black holes grow. These simulations help scientists predict what the universe should look like at different stages of its history. But when new observations arrive, those predictions must be tested, and sometimes the universe surprises us. Already, Webb's discoveries are pushing scientists to update their simulations. Models of galaxy formation are being revised. Black hole growth scenarios are being re-examined. Some theories that once seemed unlikely are receiving new attention. For example, researchers are exploring more detailed models of direct collapse black holes. Others are studying how gas flows through early galaxies might allow extremely rapid feeding. Some teams are even investigating whether early star formation behaved very differently under primordial conditions. All of this work takes time. Science moves carefully. Observations must be confirmed. Measurements must be repeated. But one thing is becoming clear. The early universe may contain far more complexity than we once believed. Pause and picture what Webb is actually doing. It is looking at galaxies so distant that their light began traveling toward Earth before our solar system existed. Before Earth formed, before the sun began shining, those photons have crossed billions of years of expanding space. And only now, in our own era, they are reaching the golden mirrors of a telescope orbiting far beyond the moon. That idea alone is remarkable, but it also reminds us of something important. The universe still holds many secrets. Each new observation reveals both answers and questions. Sometimes, the answers lead to deeper mysteries. That is exactly what is happening now. Black holes appearing earlier than expected, galaxies forming faster than predicted, structures emerging in the universe's earliest epochs. These discoveries do not mean our understanding of the universe is wrong, but they suggest the story may be more complicated than we thought, and the James Webb Space Telescope is only beginning to explore that story. Because the deeper Webb looks into cosmic history, the closer it comes to the moment when the first structures appeared. And somewhere in that distant era lies the explanation for how the universe built its first enormous objects so quickly. Take a moment and picture where we started. A telescope drifting quietly in deep space, a mirror made of gold panels, unfolding far from Earth. Its only purpose is to look outward and backward in time. When the James Webb Space Telescope began sending its first images, scientists expected confirmation of a familiar story. Small galaxies forming slowly, stars igniting gradually, black holes beginning as tiny remnants of dying stars. A calm beginning to cosmic history. But the universe had a slightly different story waiting. Some galaxies appeared brighter than expected, some seemed larger than their age allowed, and inside a few of them, Webb detected something even stranger. Black holes already enormous, objects millions of times the mass of the Sunday, yet existing when the universe itself was still young. Pause for a moment and think about what that means. If the measurements are correct, then something in the early universe was working faster than we predicted. Structures assembling quickly, gas collapsing efficiently, gravity shaping enormous objects almost immediately. Picture a city skyline appearing overnight instead of over centuries. That is roughly how surprising these observations feel to astronomers. But the story is not finished. In science, discoveries rarely close a chapter. More often they open several new ones. Astronomers are now exploring multiple possibilities. Perhaps some black holes formed through direct collapse, skipping the usual process of stellar death. Perhaps dense environments allowed black holes to feed far faster than expected. Perhaps ancient primordial black holes existed long before the first galaxies. Or perhaps the early universe itself behaved in ways we have not yet fully understood. Each explanation changes the timeline slightly, but all of them point toward the same idea. The first billion years of cosmic history may have been far more dynamic than we imagined. Stars igniting rapidly, galaxies assembling quickly, black holes appearing sooner than our models predicted. And somewhere within that rapid growth lies the deeper explanation scientists are now searching for. But this story also reveals something else, something about us, because none of these discoveries happened by accident. They required centuries of curiosity, generations of scientists asking questions about the sky, engineers building instruments capable of detecting faint light from across billions of years, and a species willing to launch a telescope far beyond the moon just to see what might be waiting in the darkness. That is what makes this moment remarkable. Not just the black holes, not just the galaxies, but the fact that a civilization on a small planet has learned how to look deep enough into space to witness the universe's earliest chapters. Think about the scale of that achievement. The light Webb observes left those galaxies more than 13 billion years ago. It traveled through expanding space for almost the entire history of the universe. Then, in our era, it encountered a telescope built by humans, a mirror floating silently in darkness, capturing photons that began their journey before Earth even existed. And from those tiny signals, we reconstruct the story of cosmic history. It is an extraordinary process, a conversation across billions of years. But perhaps the most important lesson is this: every time we build a better telescope, the universe becomes a little less predictable. New mysteries appear, old theories are tested, and sometimes the cosmos reminds us that we are still at the beginning of understanding it, because the universe does not exist to match our expectations. It simply exists, vast, complex, full of surprises waiting to be discovered. And somewhere out there, beyond the galaxies Webb has already seen, even older structures may still be hiding. Older black holes, earlier galaxies, clues to how the cosmos truly began organizing itself after the Big Bang. The search for those answers is still unfolding, and the telescope watching the ancient universe is still listening, quietly collecting light from the farthest edges of time, while we, on this small planet, continue trying to understand what that light is telling us, because we are not the center of the universe, but we have learned how to observe it, and in doing so, we have become the part of the cosmos that can look back and ask how everything began.